Thank you for watching part 1. Now, let's have a look at part 2 here. For part 2, how do we generate this here, this matrix? So I want to say, okay, we're going to fill in some values here. And so let's say I'm going to use a program called Octave. There's a fourieroperator.m. This is something I wrote back in 1989. We're going to use that. And I'm just going to first develop the idea. Octave-no GUI. So we're going to start with a certain angle, say A equals, now the angle that we're going to do is negative pi over a certain number. So let's say we want a 3-point DFT. Let's do a couple of odd numbers here, like a 3x3 and a 5x5, just for fun, because then we'll see the DC right down the center when we FFT shift it. And so let's say A equals negative 2 times pi by 3. That will give us the value of A for 1/3 of a turn. And then the index in the M direction equals 0 to 2. So don't waste too much space on the computer. And then index N equals 0 to 2. And then in this case they're the same. And then the indices equals the index generator equals index M transpose times index N, and that's our index generator. And then we're gonna let the little w equals e to the IA square root of -1 times A. And then now we simply let big W equal little w element by element raised to the index. And that's our matrix there. And you can see there that, and then if we want, I'll say W. And just to confirm that that is the matrix, let me pick a vector G, say, equals like 516, ECE 516 course, say let G equal 516. And then FFT of G, there it is, and W times G conjugate transpose is the same as FFT of G, and I might as well put transpose. Now note here I've got transpose. This symbol by itself is conjugate transpose, but since these functions are real, it doesn't really make any difference. And then now we'll let W equal FFT shift of W, and that has the DC down the center row and down the center column, and then that's the 3x3 Fourier operator that we had appropriately shifted. And so here is the function, the Fourier op function, and just implements that. And we have W, and we have exactly the same thing here as the Fourier op function. And if we take this 3x3 matrix and we just put it into right here, so we got the center row in terms of vectors, and then we're going to have the center row and the center column are all just ones, and then the fractional frequency of this row is plus 1/3, as this row, the frequency, it's going counterclockwise, and this row is minus 1/3 fractional frequency. And in fact, for three-phase power systems, this kind of transformation is quite common. And this is called symmetrical components. For three-phase power systems, we resolve it into the DC component, the clockwise component, and the counterclockwise component. So this gives you how much energy is in the DC, how much energy is turning counterclockwise, and how much energy is turning clockwise. And so that, in an ideal three-phase system, this should all be 0, these should all be 0, and this should all be 0, and it should only be going in one direction, ideally. whereas in practice there'll be some residual dissipative component and some residual component turning the wrong way. So please read this paper, published in 1918, Symmetrical Components, Method of Symmetrical Components, Symmetrical Coordinates Applied to the Solution of Polyphase Networks. So this would be the right paper to read if you want to sort of look at the original history of three-phase power resolved into the components of forward and reverse rotating magnetic fields for motors, for example. Now I've got some sockets in my house here. This is a stove receptacle for my hot tub, and this is a triplex, 3 single-phase sockets on the 3 separate phases, which is kind of a nice. And then this is a 3-phase socket here. So there's the ground is in the center, the neutral is here, and then there's 3 hot sides here. In a single-phase socket, there's a ground, a neutral, and just 1 hot side. This has 3 hot sides. So if I go from the neutral, say, to one of the hot sides, what I see, and I'll turn the light on here for a minute. What I see is there's about 121 volts here. Should be 120 volts on each of them. 119 on that one, 118 on that one, and 123 AC volts on that one. And if I measure across any 2 of them, I'd expect to see about 208 volts here, approximately. This is 211 volts across those 2, 201 volts, 200 volts across those 2, and 213 volts across those 2. So now there's slight imperfections there, and that's what that 3-point DFT does. It gives you the component, how much of the energy is turning counterclockwise positive frequency, how much of it, and how much is fighting going the other way, a negative frequency, and how much is dissipative or just wasted energy. And so with a single phase socket, the energy is equally distributed between positive and negative frequencies, whereas a 3-phase socket, you want all of the energy to be progressive so that you can get a rotating magnetic field in a motor that rotates in one particular direction, so that all the energy goes counterclockwise, for example. And of course, if you switch any 2 leads, it'll change direction, just like switching the role of sine and cosine. Now I've got a pancake or a pan pie here, and so we can think of these as 2 pi by 3 is the angle that we're going by in terms of going around there. So if I have this thing right here, 1 pi equals 2 pi. 1 pi equals 2 pi. And so this is an angle of pi, and that's another angle of pi. So if I take this piece of pi and cut it pi, so if I cut here like this, for example, this is about 1, 2, 3, 4, 5, 6. This is pi by 6. For a 6-point DFT, actually we start this way and we go down because we want negative frequencies. So we'd go like this for the 2-point DFT. So that would be A. A would be in the Argon plane. This is the real axis here, and that's the imaginary axis up here. And go around clockwise here, 1/6 of a turn or 1/4 of a turn. If we're doing a 4-point DFT, if we're doing a 3-point DFT, come around about this much here. And A, the value of A we just picked for the angle, is negative 2 pi by 3, which is this angle right here. Negative 2 pi by 3, which is equal to pi by 3, negative pi by 3. Negative 2 pi by 3 equals negative pi by 3. We actually call this teth, the Hebrew letter teth. Is what we often use. It's an old Hebrew letter like this that means wheel, and that is actually equal to 2 pi. We have that teth written this way, or if you write it in Paleo Hebrew, equals 2 pi. And so this is a teth, so we don't confuse, because we need a new way to pronounce it, because if I pronounce these they sound the same, so we call this and it's a very good pie actually. Whole wheat, whole grain, 0 sugar added. Now I have eaten about a third of that pie, which is about 2 pi by 3. So I just ate 2 pi by 3 equals pi by 3. And we can use the, for this, I use the Hebrew letter teth. We can write it in sort of Jewish square script like this, or we can write it in Paleo-Hebrew, Phoenician, ancient symbol like this, or we could even write it like this if we wanted to. It's like 2 pi's, and then which is equal to 2 pi. And we could even also, if we wanted to be creative, let's say pi by 2 equals tau, because tau sort of looks like half a pi. So this is, which is equal to by 4, which equals teth by 4. Just have a little bit of fun with some pi here. You can take a quarter wheel, half wheel, 3/4 of a wheel, or the full wheel. And so teth here is just the entire wheel. And when we're doing the 3-phase power example, we just have a third of a wheel here. And that was where we have A, which is going this way. A is the angle. A equals teth by 3, negative teth by 3, which equals negative 2 pi by 3. And that's our original angle, going clockwise 1/3 of a full turn. And we use this notion of fractional frequency. So we're going around the wheel here. Something very simple. The wheel is a very simple thing. And this is DC. And this is positive frequency plus 1/3. And this is negative 1/3 fractional frequency. And then in the 4-point DFT, we're going around here. This is 0. This is a quarter fractional frequency, a half, plus minus a half, and 3/4, which equals negative 1/4. And we could call that tau, pi. You just very conveniently symbolize them that way if we wish to. See, I found this symbol proposed for 2 pi, but I would actually call that 3/4 pi. I would say that should be 3/4 pi. We should have something like tau as a 1/4 pi. There's pi. There's 3/4 pi, and there's pi. That's how I would do it anyway, rather than this. Now let me search up Fourier operator. So if we do a search for the term Fourier operator, we get lots of nice information on that. There's a Wikipedia article on the Fourier operator. That's what that matrix looks like. This is the real part, and this is the imaginary part of that Fourier operator matrix. And then if we represent it in color, then that matrix has the color values, and 0 is along the origin. You can see in black and white here, it's 1 along the center, because it's the cosine part is all 1, and the sine part is all 0 along the center, which is represented as a mid-gray value here. 255 represents 1, and 0 represents negative 1, and mid-gray 128 or 127 represents 0 here. And you can see that center line in the imaginary part, and the center column is 0, and here in the real part, the center row and the center column are both, 1 full on. And in color, we've just simply represented that as the color shift. So we've used phase the color to represent the phase. And so this is kind of a graphical depiction of the Fourier transform. We've got something that we're taking the Fourier transform of. We multiply it by this matrix, and we get this frequency spectrum over here. And so let's kind of unpack what that means. If we go back to our search of Fourier operator, let's say right here, this shows us discrete Fourier transform as an operator. And so this is a way of understanding the DFT, the Fourier transform, as this operator. If we take sines and cosines, so let's say we take cosines to start with. Here's cosines. There's a 0 Hertz sine wave in red. We've sort of used the color order here. Red is red, orange, yellow, green, blue. Those are the orders of the frequencies. So in red we've got 0 Hertz, and 8 samples of this are all ones at 0 Hertz. A 0 Hertz cosine wave is all ones. And then if we have one cycle of a cos wave, let's say it's 1 second long and it's 1 Hertz, so then that's one cycle. 1 cycle per second is 1. And so that cycle there, you can see it's sampled here, 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 and here. And then if we have the one in yellow is 2 cycles of a sine wave, of a cos wave, and it's sampled, and those samples happen to be 1, 0, minus 1, 0, plus 1, 0, minus 1, 0 again. And if you click that link, you'll see this is broken out into individuals here. So there is DC, just sampled 8 times. This is to generate the 8x8 DFT matrix. If we take one sample of a cosine and sample it, this is what we get right here. If we take 2 cycles of a cos wave, we get 1, 0, negative 1, 0, and so on. If we take 3 cycles of a cos wave, we get these values here. And if we take 4 cycles of a cos wave, it's alternating, just 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. Now this is where it gets interesting. If we take 5 cycles of the cos wave, then it's over, we've got the aliasing, so it'll come back around, it'll wrap around in frequency, so it'll come back to being the same as 3. And if we take 6 cycles, it'll go back to being the same as 2 cycles. And if we take 7 cycles of a cos wave and sample it, it'll come back to being the same as 1 cycle. So that's aliasing. And so if we go back here now, the fractional frequency is a circular concept. So if we sample a cosine at 5/8, 8 samples per second, and 5 cycles per second, we get the same result as sampling at 3/8. This is kind of a good way to see it. Here's an example of aliasing. And so we've got the real part and the imaginary part here. If we take a cos wave at 0 Hertz, it's all 1, and a sine wave at 0 Hertz is all 0. So there it is. If we take a cos wave at 1 Hertz for 1 second, it's these samples here. The real part and the imaginary part gives us these samples. If we take a cos wave for more cycles, here's a fractional frequency of a half. Here's 4 cycles of a cos wave and 4 cycles of a sine wave. And the cos wave is 1 minus 1, 1 minus 1, 1 minus 1, and the sine wave is all zeros there. Now, if we take 5 cycles of a cos wave for the real part, and what you see here, this is a sine wave, this is the imaginary part. What you see here is that when we have a sine wave, when we've got 1, 2, 3, 4, 5 cycles of a sine wave, what you see is when you have 5 cycles of a sine wave in that same interval, it passes through exactly the same points as when you have 3 cycles in that sine wave interval. So that sine wave, that's alias. So a fractional frequency of 5/8 gives us the same as negative 3/8. This is the imaginary part and the real part. And so if you look at them individually, you get this sort of aliasing effect. So now if we take the fractional frequency of 3/4, that's the same as negative 1/4. In other words, you go 1, 2 cycles, 1, 2, 3, 4, 5, 6 cycles. 6 cycles of this sine wave is the same as if we flipped around and did 2 cycles. So see, in magenta here I've got these 6 cycles of a sine wave plotted, and they pass through exactly the same points as 2 cycles of a flipped upside down sine wave. So in this sense, the fractional frequency of 3/4 is the same as negative 1/4. That's 6/8 6 cycles is the same as 2/8 upside down, which is -1/4. 3/4 gives the same as -1/4. And 7/8, here in black, I've got 7 cycles of a sine wave. 1, 2, 3, 4, 5, 6, 7. And I've got 1 cycle of an upside down sine wave, or -1 cycle of a sine wave. And so you see that the fractional frequency of 7/8 is the same as the fractional frequency of -1/8. And finally, we see here, if we have 8 cycles of a sine wave, that's the same as 0 cycles of a sine wave. In fact, if we have 8 cycles of a sine wave, this is the imaginary part we have here. It passes through all these dots here. It's all zeros. And that's the same as 0 cycles of a sine wave. So 8 Hertz is the same as 0 Hertz when we sample over that 1 second interval, 8 samples per second. So this is right past the Nyquist rate. We've gone right around and wrapped completely around the full circle. So you can kind of see how this wraps around the circle. So it makes sense to reorder into negative frequencies. So here we have a fractional frequency of -3/8. So if we just reorder these waves into negative frequencies, so you can see I've simply taken those exact same waves here. And so what we did is the red, which was originally the first one, now we've put that into close to the center of the array and going up. So that's 0, and then a fractional frequency of -1/8, fractional frequency of -2/8, which is -1/4, fractional frequency of -3/8 in this direction. And then going in the other direction, we have a fractional frequency of 1/8. We have a fractional frequency of 2/8, which is 1/4, fractional frequency of 3/8, and a fractional frequency of 4/8, which is 1/2. So you can see we've simply reordered the waves, as I did with this example of here, of reordering them in a way that makes more intuitive sense. So in MATLAB or Octave, if you do an FFT, the command to do that reordering is called FFT shift. It just swaps the left and right sides. So it takes the left side and puts it to the right, and the right side and puts it to the left. And for a matrix, it just does that in 2 dimensions. It just swaps them this way and that way, top to bottom and left to right. So you can see, if we desire to shift the time origin to the center, this is what that row of those matrix entries are. You can think of these rows as the real part is a cos wave and the imaginary part is a sine wave, and at 0 Hertz, cos 0 is identically 1 and sine 0 is identically 0. So the real part's 1 and the imaginary part's 0 right through the center, near the center at the origin. And then going up this way, we've got a fractional frequency of 0.2468. In this is just an example here where I've got fractional frequency -0.2, -0.4, -0.6, and -0.8. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be, if you had, say, a 9-point Fourier representation. And if we take enough of these sines and cosines along rows of a large matrix, so for example a 1024-point DFT, the cosines will make a 1024 by 1024 matrix, and the sines will also make a 1024 by 1024. And if we look at the central part of it, the real part looks something like this, and the imaginary part looks something like this. And of course that's where we can put them together into this way here, and then we can see it. This is how we get the transform here, the Fourier transform, as this operator, the Fourier operator. Of course, as we can go to the continuous Fourier transform, it's like an infinity by infinity matrix, and so that just becomes that continuous image. Again, here's the 8-point DFT as a matrix multiplication, sort of visualizing or drawing out those signs. The red represents the DC, and then red is 0 Hertz, orange is 1 Hertz, yellow is 2 Hertz, green is 3 Hertz, and blue is 4 Hertz, and then it comes back down to -3, -2, -1, and so on. So if we want to put them, simply FFT shifting them puts them in the right order. Now if we separate these into even and odd columns, then we can exploit the redundancy, and then separation into even and odd columns starts to consolidate or capture some of the redundancy in this representation. And if we capture the redundancy in that representation, we can efficiently write out we can break this 8-point DFT into 2 4-point DFTs, and we can break each of those 2 4-point DFTs into 2-point DFTs, and we can divide and conquer this algorithm and make it more efficient. That's called the FFT, the fast Fourier transform. This is sort of a pictorial representation that I made showing how the fast Fourier transform can be implemented as a circuit. And so these are redundant and they're not needed, so you can take those out, and then you just need this phase factor here. So this is called decimation in time, and there's also decimation in frequency that makes this operation more efficient. And that's how the FFT algorithm in software as well as FFT chips work. So this has in a sense simplified. So this is exactly how an 8-point DFT is done as 2 4-point DFTs. The second half needs these phase factors, which are just multiplication by these constants here. And then we apply that recursively. So each time we break each FFT down into smaller ones, and that algorithm is much, much faster than doing the matrix multiplication because it's exploiting the redundancy in that pattern, the redundancy of those patterns. So 32 years ago, back in 1989, I wrote this function fourieropm that generates the Fourier operator. And so you can have some fun with that. You just give it an array size and it generates the Fourier operator. So if we go octave -- no GUI, I wrote it in MATLAB originally, but I don't use MATLAB anymore, so it still works in Octave. When Octave came out, I switched to Octave because it's open source, and I want to try to support the open source community and try to eradicate closed source if we can, ideally. So let's go image of Fourier op of, say, 1024. I take the real part of it. There you have it. Now, that's hard to see because it's aliasing so much, because it's going up to such high frequencies, the screen's even aliasing on that. So you look at the screen, it'll drive you nuts trying to understand that. So typically what I'll do is I've got a third parameter in there that lets you put in some fraction of the frequency it'll go up to. So let's look at like the center. Let's zoom into the center of it in a sense. And now it goes from a fractional frequency of -128 to +128 cycles per 1 second total if you went from 1000 to 24. So now we can see here look at it on a normal grayscale here. What you can see here, the real part, it's ones all the way down the center. You know, it's cosine, so there's ones. Cosine of 0 is 1. Now if I look at imaginary part of that, it's like this here. And so you can see the imaginary part is 0 down across the center and row and down the center column. And of course, if you want there to be an exact center column, you could always choose like 1001 points or something like that. Some kind of odd number of points if you really cared about having it be exactly, having there be an exact center row or center column. And so now in that center, it's 0, and 0 is represented as a gray value that's halfway between 0 and 255, so that would be 127 or 128 on the TV screen when you look at it. But anyway, that's a quick, simple way to understand and see the Fourier operator and really see and understand how beautiful that is. Now, if we look at this equation here, if we look at this in color, where I use a color wheel. So the way I use color to represent complex numbers is, you know, if this is the real axis, this is the imaginary axis, I'll say real is red. Real is red. I use red to represent real, and then yellow to represent imaginary, and then green to represent negative real, and blue to represent negative imaginary. So I just take a color wheel, I go through the colors from red, orange, yellow, green, blue, and violet is somewhere between real and minus imaginary. So let's say if we're going on the unit circle, red is +1, yellow is plus I, green is -1, and blue is -I. And sort of over here we'll have in between colors like violet or orange, different shades in between. The way I use colors to represent complex numbers is, let's say this is the real axis and that's the imaginary axis. I'll say that red equals real. And let's say we have the unit circle. We're going around the unit circle. I'll take +1 and I'll represent that as red. I'll take +I and I'll represent that as yellow. And then I'll take -1 and represent that as green. And I'll take -I and represent that as blue. And then in between I just interpolate the colors in between. So for example, between +1, say we had 1 + I over √2, I'll represent that as orange. Or if we had 1 - I over √2, I would represent that as violet or purple. So I use the color, I just go around the colors as around phase. In this way I can plot a complex valued matrix as an image, and so the complex valued Fourier operator becomes a color image, which I designed, and that was actually the cover art for a book that I was one of the contributors to. So now that we have the complex matrix as an image, the individual rows, and that's the DC in the middle, and then 1 cycle, 2 cycles, and what exactly, how do we think of the complex valued sines and cosines? So one way to think of this is in the Argonne plane. If I have, say, real, imaginary, and time, if we think of it, if we start out at the origin, it's all real at 1, and then it goes counterclockwise around the Argonne plane, so it goes around like that. So if we look at this complex exponential in this space of real versus imaginary versus time, sort of in a three-dimensional space, then it sort of spirals around. And if we were to look at the end of it, it's a circle. And if we look at the front of it, it's a cosine wave. And if we look at from the top, it's a sine wave. And so this sort of spiral shape is kind of what I want you to think about when you think about what's in that matrix. So let's kind of construct the elements of this matrix. So we have the straight line, just a straight line in the middle, and then we've got like this spiral thing, 1 turn, 2 turns, 3 turns, and so on. And then going the other way in the opposite direction to go down here. So if we construct that, it'll help us kind of understand that in a new way. So let's make some waves here. So what I want to do is take this pipe here as a former. I'm going to wind around it. So I want to take 12 and divide it by, let's make them 12 inches long. And so I want to take 12 and divide it by 8. So 12 divided by 8 is 1.5. So every 1.5 inches, 1.5. 3, and this is how many cycles there's going to be a cycle every 1.5 inches for the highest frequency. 1 sample, 2 samples, 3 samples, 4 samples, 5 samples, 6 samples, 7 samples, 8 samples. So they're numbered, of course, 0 to 7. So these are the samples 0, 1, 2, 3, 4, 5, 6, 7. And this 8th point is the 0th sample of the next cycle of the wave. So the wave's going to go, the first one's going to go, well, we're going to have 0 cycles here, and then 1 cycle, 2 cycles, 3, 4, 5, 6, 7, 8 cycles. And then when we have 4, it'll be easy. But when we have 3, let's do thirds, because that will be good to have. So thirds are every 4 inches. 4 inches. 8, and 12. So now come over to this side here. So let's prepare this chalkboard here. So the DC component is just a piece that's 12 inches long. That's the DC component. Now we want one cycle. So we're going to go, and we want a negative frequency to start with. So that will be clockwise in the Argand plane. So if the time's coming out this way, if this is the real and imaginary and time goes this way, it's going to be clockwise. So we're going to have one cycle of this wave. We're going to go around here once. And we'll cut that off at that point. And we've got now -1 cycle per foot because it's clockwise. And then the next one will be 2 cycles per foot. As we come out of the page, we're going to go clockwise. So that's a negative frequency. And then we're going to come around once more. So numeral 8. And we're going to be twice the way around. So that's 2 cycles. And we're going to cut it off right here. That's 2 cycles. So that is 2. So we have 0 cycles, 1 cycle, and 2 cycles are negative. Actually, these are negative. So 0, -1, -2. So that's -3 cycles. Again, clockwise is negative frequencies. That's 3 cycles. Let's also, just for fun, make one that's a positive a quarter. Grab another piece of wire here. So to go positive a quarter, we got to go counterclockwise. And note, this one's negative a quarter. It goes clockwise, and if we turn it around the other way, it's still negative a quarter. It still goes clockwise, because in order to turn this around in a way that would make it counterclockwise, we'd have to enter the 4th dimension and then turn it around. So in a 3-dimensional space, of course, as we turn it, it remains a negative frequency no matter which way we turn it. -4 cycles per foot. So if we were moving at 1 foot per second, it would be hertz. It would be -4 hertz. But cycles per foot is going to be equivalent to cycles per second, because we're moving at 1 second per foot, let's say. Now we're going to go the other way, and we're going to go around here. This time we're going counterclockwise. So this is a positive frequency. That's +1 cycle, +2 cycles, +3 cycles, and +4 cycles. So that's +4 cycles. If the spiral had 5 turns going the other way, it would sample at exactly the same locations as it does with 3 turns going this way if we sampled in 8 places, because a fractional frequency of -5/8 is the same as a fractional frequency of +3/8. So this is the same as 5 turns going the other way, indistinguishable from 5 turns going the other way when sampled that way. So we have 0, -1, -2, -3, -4, or +4, doesn't matter which one we use, and then -5, which is +3, and then we just need one that has +2 turns and one that has +1 turn. So now we've got the full transform space. So the convention I wish to choose is to put the +4 in here in the order, and then if I place these back over there where they belong, I've got the first row of that DFT matrix is here, the second row is here, third row, fourth row, fifth row, that's the plus and half, and then this row, and then this row, and then this row. So you can see these frequencies. So you can see what frequencies we have here. We've got 0, minus 1/8, minus 1 cycle per foot, minus 2 cycles per foot, minus 3 cycles per foot, minus plus 4 cycles per foot, plus 3, plus 2, and plus 1 cycle per foot. And if we FFT shift, if we put these 4 at the bottom, so keep these 4 in exactly the same order they are, but just drop them down to the bottom, and let me erase that as well to make some room for it. So we'll put these exactly in the same order down at the bottom, and that one, and then these ones in exactly the same order they were before. So now plus 1, plus 2, plus 3, and plus 4. So if we write these frequencies down, we've got this is 0, minus 1, minus 2, minus 3, and we have 1, 2, 3, 4 plus. And that is the DFT matrix, the discrete Fourier transform matrix. I'll just bring it over into the sun here. Maybe it's almost time to go up on the upper roof so we can see it better and get a nicer view of it. So yeah, the lighting I think will be better up on the upper roof this time of day. So I'm just going to come up into some better lighting. Yeah, that's beautiful lighting. Look at that. It's going to be really nice. They look really nice in the sun here. Let's see, this is a pretty good angle to view them from. Just clear off the background a little bit so this is a little easier to see. So there's plus 4, plus 3, plus 2, plus 1. So now here it is three-dimensionally. We've got 0 cycles, minus 1 cycle, minus 2 cycle, minus 3 cycles, and up this way we've got from 0 cycles 1 plus 1 cycle, 2 cycles, 3 cycles, 4 cycles per foot, or cycles per second if it's a foot per second. And so this matrix here, and this is represented as time going this way, or whatever the physical dimension of the Fourier transform is, and real this way and imaginary that way. And so you can see when we're going counterclockwise, those are positive frequencies, and when we're going clockwise, they're negative frequencies. And in fact, if you look at this, the plus 4 and the minus 4 differ slightly, and if you look at them from the end, let's look at both of them from the top here, and depending on how they're oriented, if they're oriented in one fashion, that's a cos wave. So this is a cosine wave if you look at it from this direction, and if you look at it from this direction, it's a sine wave. Cos wave versus sine wave. And same with this one. This one, if I look at it like this, it's a cosine wave. This is a cosine wave looking at it in this way. And if I look at it this way, it's a sine wave. Now it's a sine wave. It's just a question of which way I have to turn it to change from cosine to sine. So here, in order to show it as a sine wave, it's here, and it turns counterclockwise 90 degrees to get it to be a cosine wave. Whereas this one, or let's think of it this way. If I started as a cosine wave, because that's what we're sort of used to thinking as real, if we started as a cosine wave like this, it turns 90 degrees clockwise to make it become a sine wave. Whereas this one here, if I started as a cos wave, to get it to be a sine wave, you've got to turn it 90 degrees counterclockwise or 270 degrees clockwise. So that's what makes this one be a positive frequency and this one be a negative frequency. When you have only the real part or only the imaginary part, you can't tell if it's a positive or negative frequency. But together as a complex valued entity with real and imaginary parts, you can tell whether it's a positive frequency or a negative frequency. So this one here, as you can see, and from the end, when we come out of the page, when we're looking down the center of it, it's a circle. You know, when we look down the center of it, what we see is a circle. And so it's, say, starting here and coming towards us, it's going clockwise. So therefore, since it's going clockwise, it's defined as a negative frequency. And this one here, since coming towards us it's counterclockwise, it's defined as a positive frequency. So I'll put this one back here in the DFT matrix. And so there you have it. The matrix sort of realized physically with wire spirals as complex exponentials. So there you have it, the Fourier operator expressed as complex exponentials in a physical form that we can see and understand. Now I want to show you a fun and simple experiment. If I take an oscillograph, which is a machine for drawing graphs, otherwise known as an oscilloscope, and I put cosine into the x-axis and sine into the y-axis so that it draws a circle, and of course it'll go counterclockwise if I do so. And then I have this device that pushes or moves an object, so I can move this object at a constant speed while the pattern is being traced at a constant speed. And what that'll do when I take a photograph of this is it'll create a picture much like I have on that wave, wavelet, chirp, chirplet. It'll be the wave. It'll be real versus imaginary versus time. So I'll be able to see what these waves that I was just talking about look like. Now, if you don't have an oscilloscope or oscillograph, a simulation can be used on a computer. So here is a simulation of an oscillograph running on this computer with an OLED screen, which has nice high contrast ratio. So it'll show up. So there's an upside down cosine wave. A cosine wave. And if I turn upside down, and if I turn upside down, look at it from upside down, there in fact is a cosine wave. So this bike rack here, it looks like 6 cycles of a cos wave, and I wanted to just show that by looking at a cos wave. So I have a signal generator connected to my oscilloscope, and one of my favorite oscilloscopes is this HP 1200. But unfortunately, it does not have a horizontal gain knob on it, like many other scopes do. You know, most scopes, even this one from 1934, has a horizontal gain, horizontal and vertical gain. This has horizontal and vertical gain. A lot of these other scopes have horizontal and vertical gain, but they left that off. There's a few things, certain things missing from this scope. It's got nice balanced inputs, but not a horizontal gain. So what I did is I did an XY plot here of this signal generator. So I have on the x-axis, I've got a sawtooth at 2 kilohertz, and on the y-axis, I've got a sine wave at 12 kilohertz. Six cycles of a cosine wave. If I look at it from the end, it's more or less a circle. And then if I look at it from the side, tip these over, just careful not to scratch them. Just gently set them down on the ground there. And now we have a sine wave. 6 cycles of a sine wave. Okay, now let's carefully put these back where we found them.